Today, I'd like to introduce our recent works about explainable AI for computer audition in digital health from local to global perspectives. As we know, in the domain of digital health, it's an interdisciplinary field of healthcare and digital technology. It can include telehealth, mobile health, and personalized medicine. As the second biggest sense of human to the world, hearing is very important for us in our life. Computer audition combines signal processing, machine learning, and deep learning together to perceive the sound in the world. So today, I'd like to introduce the explainable AI in the applications of computer audition in digital health. There could be many applications of computer audition in digital health, such as COVID detection from respiratory sounds and the speech emotion recognition, depression detection. Next, we will mainly focus on respiratory sound classification. So in the following, I will introduce our works according to the following content: explainable AI, local explanation, global explanation, and finally, conclusion and outlook. As we know, explainable AI can help us to build the trust between machines and physicians and patients in digital health. In the recent works, there have been already many local explanation methods, such as model agnostic methods like LIME and model-specific methods like attention mechanism, which can learn the weight of each feature unit in the feature maps. However, local explanation can only interpret models case by case. It can't generalize the characteristics of the model for the whole data. Therefore, in our recent work, we tried to learn the prototypes from a whole data for respiratory sound classification. Prototypes could be understood as the most typical samples in each class. How to compare the prototypes and understand the model? We can compare the prototypes and an audio sample. This could be helpful for physicians. And informed prototypes could be a natural sample, which is searched from the original data, but the natural sample can only partially represent the class. It could be also a synthesis sample. Therefore, the synthesis sample can contain most of the characters of each class. Therefore, physicians can understand more about diseases. In this approach, we tried to learn different kind of prototypes. The first type is prototype 1D, which is vector. Let's assume the number of classes is L and number of prototypes in each class is N. So we finally will learn a group of prototypes of capital P, L, and single prototypes type, we represent it as PI. In the framework, the similarity is computed based on the learned features F, X, and the prototypes. The cosine similarity here is used. However, prototypes 1D contain limited information of the data. we assume that 2D prototypes can better represent time frequency information. Therefore, we can visualize the prototypes for further explanation. So in this work, the three types of 2D prototypes were used with the three similarities, including the element-wise similarity. It computes the similarity scores between each pair of time frequency beings in F and P. And we can also compute the average score across the similarities between all of the time frequency beings in P and each being of Fx. The maximum similarity means that we selected the maximum score from all of these similarities. So we call these methods as prototype 2D with vanilla similarity. Comparing to the prior two prototypes, attention-based similarity could learn weighted similarity scores. Therefore, we hope we can have better performance with these learned prototypes. So element-wise similarity and maximum similarity were used in the attention-based similarity here. So based on the prototype 2D with vanilla similarity, we use the sigmoid function on the similarity between Fx and P and further use it as the weight and multiply it with F and P together. Maybe we are also very interested about how to train such a model with so many similarity scores. So the loss function here is defined as this equation. It contains two parts. The first part is typical classification loss. If you have other tasks, you can also use other loss functions. The diverse loss function here aims to make the different class of prototypes to be far away from each other and prototypes in the same group to be close to each other. So we call this as the diverse loss here. In this work, the database of the ICBHI challenge in 2017 was used for the respiratory sound analysis. All of these breathing respiratory sounds, also breathing sounds, they are annotated as 4 classes: normal, crackle sound, wheeze sound, and both crackle and wheeze. Then let's see how about the results here. When we compare different prototype number in each class, we tested from 1 to 5. We found that the performances are comparable when n is 1 to 5. So if we learn only one prototype for each class, it could also very well explain the model and have a very good performance, especially. In the similarity comparison, we found that the prototype 2D with vanilla element-wise similarity has a better performance than the others. This could be because it has a very good capability of generating prototypes with time frequency information compared to prototype 1D. And especially, although the attention mechanism is very promising here, but it has more parameters than the prototype 2D with vanilla similarity. Therefore, finally, we got the best performance by the prototype 2D with vanilla element-wise similarity. Then let's see how to explain the learned prototypes. These 4 log-now spectrograms are and not the learned prototypes, because they have very small size as they are at the final convolutional layer. So here we projected the learned prototypes into its closest original sample. So we have the 4 samples in this slide. You can see that normal respiratory cycles are regular, while the others are quite different. They are not regular. And the Weiss log-mel spectrogram has smaller coefficients on a range of mel frequencies than the crackle one. This is probably indicating the Weiss song is weaker than crackle, because crackle songs, if you listen it, it's like an air brake. For the both class, it will be difficult to explain because it combines both Weiss sound and crackle sound. Apart from prototypes, prototypes can represent each class. There could be also some data samples which cannot be very well captured by the model. So in another work, we try to find out such instances as criticisms. Criticisms are often very close to the decision boundary. So it's very easy for a machine learning model to give mistakes for these data samples, as we can show in this figure. And criticisms can also help avoiding overgeneralization and bias by allowing human experts to assess the misclassified samples and outliers. In this approach, learning method was not used because learning prototypes and learning criticisms in the meanwhile will take a lot of time to train the model. So, and we also found that adversarial attacks are very promising and efficient to find out both prototypes and criticisms. It can unify the example-based explanations. Therefore, in this work, we assume that prototypes are the most difficult to attack for an adversarial attacker. Therefore, in the framework that when we give the fake data and to the model, so we found that it can still be correctly classified after a maximum setting of IMAX stack of IFGSM attacks. The IFGSM attack here is the iterative FGSM, which use the theory of the gradient of the model to attack the machine learning model. It is a white box adversarial attack. And criticisms, we assume they are very easy to attack because they are at the decision boundary. So criticisms could be assumed that they can be misclassified after only one step attack. In addition, attention mechanism was used to further verify whether the learned prototypes and the criticisms can represent the right characteristics of different classes. So the latest CN model is also used here to preserve the size of feature maps. Therefore, we will visualize a better feature maps with a high resolution. We will see the feature maps next.
Yeah, hi Zhao. So, yeah.
Okay,
yeah.
I will, yeah.
1 minute, please.
Thank you. Mm-hmm. Yeah, we found when we compare different iteration step I and the perturbation scale epsilon, we found the performance are different. So it's very important in the experiments to select an appropriate I and epsilon. Then we can also visualize the prototypes and the criticisms. And in prototypes for the classes normal, critical, and with, they can represent different characteristics of the three classes, as these are consistent with the work as mentioned before. And criticisms can only present typical, partially present typical characteristics of the songs. And we also use attention to emphasize the contribution parts of each class. So in conclusion, prototype learning and selecting prototypes and criticisms via adversarial attacks were used in our prior studies. In the future, prototypes and criticisms in form of audio signals could be learned. Therefore, we can listen about them and distinguish what characteristics. Yeah, and other types of explanations could be also explored, such as counterfactuals. These are the code of the two works, and thank you very much for your attention.